Okay, thank you so much. All right. So I am enjoying the conference. I hope all of you are also doing the same. And I am seeing a little bit of Delhi also, because I stay in NPL campus and every day I travel 1 hour. So my day starts at 7:30 real for the conference, and I finish at 9 o'clock. I am not working so much when I am in Kanpur. So my formula is 8 hours. I tell my students also, and particularly for the students, if you work 8 hours, dedicated, focused, that's more than enough. So I'm from Kanpur, and I will talk about 3 compounds. And we have already listened a lot of review talks and introductory materials, introduction to topological materials. There are dedicated sessions, so I will not spend time on the introduction part, but I will focus more on the materials. And so these 3 materials, one is cerium gallium silicon, where we found large anomalous Hall effect. And I will talk a little bit about whether antiferromagnet or ferromagnet. There were a lot of struggle with the physical review referees about the nature of magnetism. And the next compound is about gadolinium, rhodium, lead. So this is like spin-only system. So the gadolinium. So all are basically rare earth compounds. Yeah. This is the group, and I would particularly like to focus on this person, Rajesh Swami. This is primarily his thesis work, part of the thesis work. Daluram is now a postdoc in IISER Bhopal. Mandeep is in Korea. And these are my theory collaborators, Kanchana from IIT Hyderabad, and these are 2 students, Sonali. So that's the beginning. So this slide I will skip, because topological materials, you have seen it all. There are different kinds, like depending on the degeneracy. So the Dirac semimetal, they are all degenerate, and when their degeneracy is lifted, you can get Weil semimetal, nodal line semimetal. We have learned all this. Then these compounds were these 3 compounds that I consider, topology and magnetism. They interact somehow, yeah, and that gives rise to different interesting effects at low temperature. And this slide gives some example what can happen at low temperature when these topology and magnetism are together. One example is like this is like gadolinium, gold germanium, anomalous Hall effect, europium cadmium to arsenic 2, anomalous Nernst effect. Nernst is like thermal version of Hall effect. Yeah. And then also we have like quantum anomalous Hall effect. So like quantum Hall effect and anomalous version, which means without magnetic field perhaps. Then we have the europium silver, arsenic, gadolinium platinum, where we say chiral anomaly. So like the typically the signature is negative magnetoresistance, and this charge pumping from one cone to another cone. The other thing is like some of the material like europium, indium to arsenic 2. People talk also about axion electrodynamics and the gravitational anomaly. So there are a lot of things that these magnetic topological materials can show. This one, actually, I will not read this slide. The rare earth compounds, they are many interesting physics, starting from heavy fermion superconductivity, which is like one can say, the mother compound for high TC cuprates. the mechanisms are similar. But I think this slide can be replaced by a cartoon of Xi Jinping and Donald Trump. I think that would be the best slide replacement, why rare earths are important or rare minerals are important, right? So let's go to the first one, cerium gallium silicon. This article was published, this work is published in Physical Review B in last year. So there were already some report, polycrystalline report, and then there was a single crystal where they claim that it's a semiconductor kind. Earlier report was saying metal. So already there is a hint that the gallium and silicon, they can be like there can be compositional variation. Sometimes some sample can be gallium deficient, some can be silicon deficient. So it's possible to tune their properties. So it's important that we make a crystal of proper stoichiometry, which we succeeded. And this is a very simple, it's not difficult to grow this crystal. We grow these crystals from gallium flux basically. So you may call it like self-flux. Yeah? There is no extra element. And this is the crystal size is quite reasonable, 2 to 3 millimeter. Thickness, of course, is small, maybe 0.2 millimeter or something like that. So we did X-ray composition, everything looks quite good. And now comes to the magnetic data. So let's see here. So this is because we have the plate-like crystal. The c-axis is perpendicular to the plate direction, so one can apply magnetic field in plane, in parallel to the plane of the crystal or perpendicular to the plane of the crystal. So the structure if you see the B parallel C, for example, it increases, goes to a maxima, and then decreases, and then some kind of a plateau, and then saturates. So typically, if it is compensated pure antiferromagnet, you will see that maxima and then sharply decrease towards 0 as you cool the sample to lower. That's not the signature, and it's not like a ferromagnet also, where it will increase and then saturate. But you see the M versus H. So for B parallel AB, rapidly increases and then saturates. B parallel C is slower and then kind of quasi-saturation. So all these gives a hint that it's antiferromagnet, but not compensated pure antiferromagnet. And which is also true, visualized, can be realized also from the M versus H type. So at low field, it's like linear increase, but then it saturates. There is more detail that more detail about the M versus H. That if you do the DMDB, for example, or DMDH, you find that there is some metamagnetic kind of transition. Okay. We also, because the cerium compounds, depending on the crystal structure and the environment of the cerium atom, it can the properties can be affected by the crystalline electric field. So in the lattice there are ions, and they can create some electric field, and that influence the properties of the crystal. So it determines in which direction, how much will be the magnetization, which direction will have more. So one can use these magnetic data or the heat capacity data to analyze the crystal field levels also. So which we have done, and we get this kind of from the magnetic susceptibility. This is our tentative level scheme, that ground state is doublet, and then second doublet is at about 190 Kelvin, and the third one is about 288, close to room temperature. So cerium, it has J equal to 5/2. So it has only one electron, it's trivalent. So one electron and F electron, so which means L equal to 3 and one electron, so S equal to half. So using this Hund's rule, you can get that J equal to L minus S, that will be 5/2. Okay, so 5/2 means the total degeneracy will be 2J plus 1, that will be 6. So one expects 6 levels. Yeah? And from the magnetic susceptibility analysis, we propose that this can be actually directly checked using inelastic neutron scattering. So neutron scattering will be able to further confirm whether this proposed level scheme is all right or not. But within whatever data we have, this is consistent with the heat capacity data. So heat capacity also confirms the magnetic watering. Okay, we measure down to 2 Kelvin. Maybe further low temperature will give even better. We also, from heat capacity, using this C by T versus T, and then you take the entropy. So you can check the entropy, and entropy also is consistent with what the proposed crystal field scheme, because you see that there is one RLN2 which is happening at about 10 Kelvin. Okay, our first level scheme was far above that, and then RLN4 we are getting here at about 100, and then RLN6 we are getting within 300. Our all 6 levels were between, the highest was about 288 Kelvin, so which is consistent. Then we did also the, it's going fast. Yeah, this is the electrical resistivity and magnetoresistance. So electrical, there is no clock in this. You should put a clock at the behind. Okay. So the resistivity is like decreasing with decreasing temperature as expected for a metal, and then this one is reduction of spin disorder scattering, okay, at the magnetic order, and also the magnetoresistance we measured both for B parallel AB and B parallel C. The current is perpendicular to C, means thin crystal, so we can flow current only in the AB plane. Yeah? And so what do they say? So it's like this is 10 Kelvin, okay, 8 Kelvin, and this is 2 Kelvin. So 2 Kelvin data, if you see, there is a decrease, and then 2 Kelvin, so it's like this is 30 Kelvin, and then this one, yeah. So it comes like this, and then, so there is some kind of a crossover from negative to positive at 2 Kelvin. Yeah, and this one, if you see the B parallel C, also it's like there is a increase and then decrease. So initially there is a positive, and then at higher field it becomes negative. So there is a change from positive to negative. The residual resistivity is not so great, it's 1.5. So perhaps there is some kind of disorder, and which is expected because gallium and silicon they can have some not so much size difference, identical. So there can be some disorder that might be responsible for low residual resistivity. This is Hall effect. And Hall effect also, like we find that there is this the Hall signal. It cannot be only, it's not like linear in field. So if it is only normal Hall effect, this will be rho h, the Hall voltage will be linear in magnetic field. So here we could analyze in terms of one linear component, but there is something proportional to magnetization. Yeah? So one requires these terms proportional to magnetization, and that's why we call that there is anomalous Hall effect present in this compound. And the Hall effect also we analyzed further, and we find that the Hall conductivity, there is one part which is proportional to the resistivity, and one part is proportional to square of the resistivity. Okay? So the proportional to resistivity, that is like coming from skew scattering, and this is like intrinsic contribution related to topology of the material. In collaboration with Kanchana, Professor Kanchana of IIT Hyderabad, so they did some calculation and they proposed that this is a possible topological material. But confirmation we don't have, because 5 minutes, yeah. So confirmation we don't have, but RPS can be measured, and that can confirm this topological property of this material. Now I have only 5 minutes, so I will skip this what I have already told, the part on summary. The second part is gadolinium rhodium lead. This compound, this is a pure spin compound. Good crystals were grown, and here I will just highlight, these are standard things like antiferromagnetic ordering, susceptibility. These are the effective moment is what we expect for S equal to 7.5. But I would like to focus only on one thing, that is that with application of magnetic field, we find some field-induced transition, okay, which is clear from this M versus H data, okay, and DMDB or DMDH can really give you at what field, and from those heat capacity also confirm the bulk nature of the magnetic ordering. Like previously we did resistivity, magnetoresistance, but I will come to the particularly interesting feature of this compound, which is like the topological Hall effect. So Hall effect, like previous compound, cerium compound, we could fit with two terms only, rho naught B plus something with magnetization. Here we tried that and we could not succeed. So we need some additional term which we attribute to this last term. We call it topological Hall effect. Yeah? And from all these data, susceptibility, heat capacity, resistivity under magnetic field, we draw this phase diagram. And this region is where the topological Hall effect. So we believe that in this region of HT phase diagram, the magnetic texture is such that it produces topological Hall effect. So again, neutron diffraction and arc phase will be good for this compound. Just last 2 minutes, I have 2-3 minutes. I will quickly go through the last compound, europium silver to germanium 2. So this is the like the europium compounds. It's like similar like gadolinium. They are also spin only system, 7 electrons, S equal to 7.5. And the interest is that, so long time ago, like cerium, there are so many heavy fermion compounds, heavy fermion superconductor. Europium also can fluctuate between 7 electron and 6 electron. 7 is J equal to S equal to 7/2, and 6 electron version is like J equal to 0, L equal to 3, and S equal to also 3, L minus S gives you cancellation. So non-magnetic it becomes. So it can fluctuate between magnetic and non-magnetic, which is also true for cerium compounds. So if cerium compounds can show a lot of interesting effect, why not europium? So this was the first work we did, and europium copper to germanium to silicon doping we did long ago, and in that context, and also in the context of topological material, we synthesized this compound. And I will just go to the main result. So it's also antiferromagnetic, and like heat capacity also confirms the bulk nature of antiferromagnetism. And this is the magnetoresistance is not so much, it's only 1 or 2%. Again, RRR is not so great. But this is my last slide. Yeah. So other than this europium silver to germanium 2, we worked also on europium gold arsenic, which was published in 2022 in Physical Review B. And recently, 2024, we published this compound, europium gold antimony. And I would like just 1 minute to tell the story about this europium gold antimony. So, yeah, so the interesting thing is that, because this gives a little bit of motivation for the students also. So this compound was actually, I got this compound when I was doing PhD. I was working on 334 compound. And I wanted to make europium 3 gold 3 antimony 4, and I got 111. But we did not do much. We just left it there, because after that the borocarbide came, Professor Bhaskaran will know, and then we all got engaged in that interplay of magnetism. But now, because I was working on this topological, so I said let us look this compound also. And we successfully prepared, and then at that time our PPMS was down, so I had a collaboration with Prabhat Mandal from Saha Institute. I wrote to him, can you do some measurement with your PPMS? He said, look Zakir, I already have some, I am working on this compound with another person, so I cannot do that. I said, okay, please don't do that. Yeah? And then he's still a good friend, and we collaborate even now. But we measured, so I took help of Sundaresan from Jawaharlal Nehru Center, and he helped with the PPMS measurement. We published a paper in this 2024, yeah? And after that, there were three more papers, and the most recent one is on a topic where they say europium gold antimony is a possible alter magnet. So you see how things evolve and how much struggle one has to do to take things forward. Yeah? So if you are doing experiment in India particularly, you have to struggle until you retire. I am struggling even now. Yeah? Okay, thank you so much. Yeah.
Thank you, Professor. Thank you, Professor. Thank you, Professor Sen. Now talk is open. If you have any questions, then.
Yeah.
Thank you for the wonderful summary of the past and the present and the future. I have a question about the cerium system. The well-known cerium nuclide, which exhibits double staircase and as a function of magnetic field.
Cerium nickel.
The nuclide.
Cerium nictide.
Yeah.
Yeah. Which one?
I think CP2.
Acha, okay, okay.
It exhibits double staircase, magnetic plateau. So
Yeah.
very highly structured. So I was wondering, because I could see some plateau in one of your cerium system, gentle plateau. So I wonder whether you are focused on that. Maybe we can chat about it later.
Okay, okay. Cerium, actually cerium antimony is the field dependence of cerium antimony is there are I think seven
Exactly.
like seven staircase they call devil's staircase. Yeah. So here also maybe some
That's what I was
yeah
spoken.
right.
Okay, thank you for the nice talk. So I want to ask that for the cerium compound, so you said that there is some Dirac point, right? Dirac point for the topological
It's a possible topological material, yeah. But we have not done any RPS. It's based only on the electronic structure calculation.
initial calculation has been done.
Right.
So I wanted to ask that which band is crossing the making the Dirac point, but from cerium band or gallium band to
That will be difficult for me to answer immediately.
What is the typical lateral size of your europium gold antimony crystals?
It's about 2 to 3 millimeter cross 2 to 3 millimeter,
Okay.
and thickness will be 0.2, 0.3. Yeah.
And can one cleave this material?
Cleaving we have not tried, but I guess so. Cleaving should not be difficult, I think.
And I
Yeah.
was just wondering, do you have any theoretical band structure of this material in your slides?
You want to see those crossing points? Let me.
If you
Yeah. I have you in mind for the RPS.
Okay.
Okay. I have you in mind in RPS. Here it is.
Oh, this is the cerium one. I was wondering about the altermagnetic candidate.
Acha, Walter magnetic I don't have.
Okay.
I did not put the slide.
Okay.
That's just part of the story of europium compounds.
No
Yeah.
problem. Thank you.
Yeah. But we have done band structure also, so you can just take a look at the PRB paper, our PRB paper, which is published last year. Yeah. Band structure is done. Yeah.
Thank you, sir, for a nice talk. So just two questions actually. So the first time you mentioned in cerium compound, so it might have some anti-site disorder for the low RRR ratio. So like, does it change the structure much? I mean, does it tune the space group? Like when there is some anti-site disorder?
Could be. Yeah, people say, say for example, when we do say silicon doping at germanium site, there are two kinds of ideas. One group says that, okay, nothing is changing except then that the cerium is creating some chemical pressure.
Okay.
Some other people who are more strict, they will say, oh no, germanium and silicon are not same. So you treat them separately. So that means the symmetry also might change.
Like it becomes very difficult to differentiate with just XRD alone.
Yeah, with simple XRD it will be very difficult. One has to do dedicated structure with high resolution synchrotron kind of.
Okay.
Yeah.
So regarding the magnetism, like you claim it to be antiferromagnetic, but the experimental data shows like it behaves more like a I-zinc type of ferromagnet, because the easy axis saturates very easily, but the hard axis saturates after some critical field which is very large compared to the easy axis.
Yeah, that's where we had a struggle for 3 months with the referee. Referee wanted us very much to. He said everything is fine. You just don't talk about antiferromagnet. You say ferromagnet.
Okay.
And we say, how can I say ferromagnet when I know at very low field it has all the signatures of antiferromagnet, and with field I am seeing that field induced metamagnetic transition.
Okay.
These are not consistent with ferromagnet. So we did not accept the referee. Finally he or she agreed.
Okay.
Yeah.
So no neutron has been done.
No neutron has been done. We will contact some. Yeah.
Okay, thank you, sir.
Yeah. I think the neutron. I am fortunate. There is RPS, and chair is neutron.
Thank you, sure, sir.
Yeah.
We can do that.
Yeah.
One last question.
Thank you for the talk, sir. So you talked about the topological Hall effect.
Mhm.
So in your sample, what is the origin of the topological Hall effect you're talking about?
Okay, so that's what I gently said, that that the magnetic texture. So it is happening in certain field temperature region. Yeah. So in that region, the magnetic texture is like skyrmion, you know, like
Yes, I know.
yeah. So
is it
some.
appropriate to say like without any imaging and saying?
That's what I am saying. That I am saying that there is signature of topological Hall effect. Magnetic structure requires some particular. So I am saying that there is a something which needs to be confirmed with further neutron scattering or X-ray scattering. Yeah.
Conjecture.
Right. Yeah.
Just conjecture.
Right. Yeah.
Yes, I made this.
Hmm.
You talked about nickel borophosphate, old friend. Recently, there is a lot of saying bilayer nickel superconductor. Bilayer.
The recent ones,
Yeah.
the nickelate, the lanthanum nickel. I was actually thinking of asking you that,
Okay, let's start.
like, what is your impression about this? Because this is a very interesting new development. Like cuprates, there was a talk by Subir Sachdev, and he did not mention, of course, about nickelates, but nickelates under pressure, it has a TC of 80 or 90 Kelvin, and it seems some group is able to stabilize in thin film without pressure. There are a lot of things perhaps to do in nickelate. Yeah.
I understand there are many questions, but since we are running against time, so maybe, sorry, we thank Professor Hussain once again. Thank you.
Thank you.
And next talk